At this time, I'd like to welcome to the stage the members of the tire modeling debate, discussion, throwdown, workshop. But look, there's only one guy that could really pull this kind of thing off, to get all these people on stage and to be able to have this type of Q&A and interaction. And that guy's Mike Stackpole. Mike, we've had the pleasure of working with for a number of years now and having a strong collaboration with him. He's just an all-around great guy, too. You can't say anything bad about Mike. So, Mike, if you and your team would like to come on up to the stage, the floor is yours.
Come on, guys. Come on up. So they're already arguing back in the hallway. As you can tell, it's very difficult to corral this group. You guys, wherever you want to sit. So thank you very much for being here, and I wanted to thank Gary and the VI Grade folks for allowing us to host this panel. You know, this is, as far as I'm concerned, the premier tire model developers in the world, and I really appreciate you guys traveling as far as you have traveled for this. So again, I appreciate that. Please know that we're supposed to be a half hour, and last time this group got together, it was not a half hour. That's all I can say. So I've got a couple of questions that I'm going to ask them, and then hopefully we will have enough time at the end to welcome your questions in. So I'm going to get started a little bit. So the title of this panel is State of Tire Modeling for the Virtual World. So over the course of the next 30 minutes, we'll be discussing development and implementation of tire models for the virtual environment and the challenges and opportunities you have all encountered developing tire models for simulators. At the conclusion, like I said, we're hopefully going to have some time for the audience to ask the panelists questions. I'm going to start with the introductions here, and I'll start down the end. Francesco Calabrese? Nope, Calabrese, there you are. I'm sorry, I apologize. See, I went in alphabetical order, and that just messed me up. So Francesco received a master's degree in mechanical engineering at the University of Naples, Italy. Since the end of 2013, Francesco works as a research assistant at Fraunhofer Institute of Industrial Mathematics in, you threw that word in, didn't you? Kaiserslautern. Okay.
Kaiserslautern.
Thank you very much. He's part of the CD Tire model development team with special focus on real-time applications, advanced structural modeling, and virtual tire development.
Thank you, Mike, for the introduction.
Absolutely. So I'm going to continue to go in alphabetical order, and I apologize, but Gerald Hofmann. Gerald graduated in mechatronics at Munich University of Applied Science in 2003. His diploma thesis on aircraft landing gear was the first industrial product using MBD software. After graduation, he joined Intech GmbH as project and development engineer in the SimPac automotive department. With focus on full vehicle and drivetrain NVH simulations, he developed customer-specific methods and worked on product customization, mainly in the area of commercial vehicle, R&D, and motorsports. As product manager for F-Tire interface in SimPac, he was responsible for high-frequency tire and road modeling applications. In 2009, Gerald teamed up with Dr. Michael Gibson, our friend, and established cosin scientific software to advance development and application of F-Tire, the leading higher frequency tire model in the market. From 2009 to 2020, he, together with Dr. Gibson, were responsible for product development, Q&A, business processes, and licensing. And from 2020, you are now the CEO at cosin Scientific Software. A lot of responsibility.
Thank you so much.
Yes, sir. Mr. Henning Olsson. Since joining Calspan in 2015, Henning has been developing and implementing modeling technologies to help Calspan's customers bring new and innovative tires and vehicles to market faster than before. With extensive experience in the use of CAE and simulations to understand and predict tire performance, Henning works side by side with global customers to make tire testing and modeling more accurate, repeatable, and cost-effective. Prior to joining Calspan, Henning spent several years as a vehicle dynamics engineer in high-level motorsports. He received his Bachelor of Science in Engineering from Dartmouth College and his MS in Automotive Engineering from the Royal Institute of Technology in Sweden.
Thanks, Mike.
You're welcome, sir. Andrea Sammartino. Andrea works as a project coordination manager at MegaRide, a spin-off company of the University of Naples, whose target is the development of vehicle dynamics and tire road interaction physical models. Andrea's daily work focuses on model development, parameterization, and calibration of the optimization of tire performance in motorsports, in driver-in-a-loop systems, and in smart mobility scenarios. His most recent work experience has also allowed him to specialize in business development and partner engagement, supporting OEMs in the development of testing methodologies and tire digitalization phase. His efforts in the growth of the startup have led to Tire Technology of the Year Award in 2018 and a Development Tool of the Year in 2019. Did I get it all right?
Yeah.
Okay.
Thank you, Mike.
You're welcome. So I'm going to start asking some questions, and Gerald, you are the first recipient of a question. What I would ask would be just go ahead and answer the question, take what time you need. I would invite then the rest of the panelists to support all of your answers.
I hope so.
So Jerry, what do you feel are the requirements for a tire model to ensure that it is capable of performing fully in a real-time environment? 2 minutes. No, just kidding.
2 minutes. Okay, so don't blink, could be over. Yeah, I think they could best be answered by looking at where we are coming from. So since the vehicle CIE tools have evolved, there's always been different stages of maturity or how much of the physics are kept, and every evolutionary step of these tools brought another level of complexity also for the tire models. And this is the reason why today we are having so many different levels of simplifications. Some of them are still in use, and there is a legitimate use for them as long as the questions you are having is inside the valid range of what these approaches are made for. But then came the driving simulator, and the driving simulator gives us the great opportunity to be no longer restricted to a particular way of looking at things. So bridging the gap between simulation and reality, that also means that you can give the car to someone and let him assess the car under what aspect he likes. So when you're cornering and you concentrate on how the vehicle behaves, then this could be considered handling. While if you concentrate on the vibration coming from the vehicle, this could be considered ride. So just like the real car and the driving simulator, the boundaries are blurred. So you cannot continue to think in application cases and pick the right tool with the least effort and cost for this particular application case, because you have everything at the same time. Cornering, and there comes a pothole, and you want to study how the vehicle reacts to that. So this is no longer possible, and that gives the requirement, as far as I understand it, to the tire model. It must be seamlessly integrated in the development tool chain. So don't have so much time spent on making simplifications. Put more effort in it as a one-time effort, and then just like for the real tire, you have something that can be used without considering the boundaries of its validity so much. And yeah, having all this under the real-time environment, that means a very complex system that's demanding in terms of computing time and also implementing it. It brings your vehicle to a completely new domain. Coming from non-dynamic tire models makes a closed-loop co-simulation out of it, so that's challenging, but it's worth the effort. So what you get out is much more than you put in, and so the conclusion is, for a tire model that satisfies all these requirements, it must provide you a seamless tool chain from your offline simulation up to the most advanced discipline for the driving simulator, without any transitions or other simplifications that do only apply for a particular use case.
Awesome. Thank you, sir, very much. Guys, we have about a minute and a half here. If you want any other discussion, or we can move on to the next question. I know you want to say something.
I think one thing that comes to mind, though, is also looking at the history of these tire models. Several, in terms of real-time performance, a lot of these models were developed in a time where real-time wasn't a requirement. Right. So it's kind of, thinking about what does the future bring too, is can we reinvent some of these things where real time is number one on the requirements list and not an afterthought, but just where we've evolved these complex model into something that's real time capable.
Awesome. All right, well, I'm going to move on to the next question. Thank you. Francesco, question for you. What challenges have you encountered when developing and integrating tire models for a Dale & Hill simulator, and how did you address these challenges?
Yep, in principle, we at Fraunhofer, as let's say, cosin, we develop a structural tire model. So the philosophy respect to magic formula, for example, models or semi-empirical model is completely different. And integrating such a tire model, let's say the first step of complexity is that we have around 150 dynamic degree of freedom that has to run real time. So the first step is to ensure the numerical stability of that. That is done through, for example, an embedded co-simulation scheme, and in which the vehicle is running on 1-3, and the tire has to run to a lower step size. It means 1-4. And what is the benefit of the fact that the tire runs on such a small scale of step size is that you can simulate by having the physicality of the belt, the fact that the belt is flexible and so on. You can simulate accurately until 150 Hertz. You can envelope physically, in principle, obstacles. And in principle, you can simulate the longitudinal dynamic around 30 Hertz and the vertical model around 90 Hertz. And this is absolutely not trivial when coupling such a tire model with a vehicle model like Viega real time. And this has been a big part of the work. Of course, the benefit of this is when coming to tire design, because in a structural tire model, then you can use this structure, all this degree of freedom, to feature what is a real tire. In principle, respect what is a full fitting scale model like magic formula, for example.
Excellent. Thank you. Guys, any thoughts? Please.
Yeah. I wanted to shift the focus regarding the challenge that we have at the DIL on the step after the implementation. So on what we should do and what we could do in order to get the most of this experience. So I will shift also the focus on the relationship that we have with the driver. There is a lot of technical part in this stuff, but there is also a human component. There is always a lot of work that we do on the experimental data. So before going at the DIL, we have to work on the sole tire module, then coupling the tire with the vehicle model in offline environment, and then we reach the DIL target. And one of the biggest challenges that we face when we do this process is always in bridging the gap between the offline context and the online context. So what happens when you follow the data and you reproduce the experimental data using that model or calibrating the model, and what you have when you work in the DIL, coupling the subjective feelings with the objective stuff coming from the work that you have performed on the experimental data.
Right.
There is always a slight difference between the model that you get from the experimental data and the model that you get after the validation of the driver. And it's always difficult to find the answer to this mismatch. Right. It is probably due to the fact that there is a human being in the loop, or maybe that there are, for example, conditions that are covered in the DIL environment that are not covered by the experimental data. So this is another big challenge that engineers and technicians have to face when working in the DIL. So I think it's interesting also to remark this point in terms of challenges that we daily face.
Excellent. Okay.
I think this point also open to more physical tire model, because in principle, when using semi-empirical model, you get a set of data, and this interpolates quite well, but does not extrapolate quite well. Right. And that's when physics come into play. It means you can use physicality and structure to reach, let's say, things that you could not reach during measurements, for example.
Mm-hmm. And it's also important to really to stress that simplified tire models can only do simplified things. That seems like, that seems obvious, but when you see how customers are using this is mostly negotiating. I am trying to stretch the boundaries of the simplified tire models as far as possible, just to save time and cost. And then there is this certain expectation that if you cross these boundaries of the limitation, then the result might be less accurate or whatever it is. But what it actually is, it's totally random. So because you're trying to read out something from the tire model, that's not even inside it's not covered by the concept. And technically you can do this, and this is what the tricky bit is. You can do this technically, and then you drive up a curbstone with a point follower model, and then you look at the vertical forces, see some oscillations, and take it as a proof that it's okay. But what damages the suspension is the lateral force acting on the tire, and the point contact follower model doesn't even have a concept of a geometry contact in the leading edge of the tire. So when you look at the longitudinal forces, they are not even there. And what you see in the vertical direction is actually just a suspension oscillating. And so this is why there is so much attempts always to stay on as simple as possible, because people are afraid to enter this new domain of simulation. And the story that we are trying to tell is, when you have solved this one-time effort and you have the most comprehensive model, there is absolutely no reason not to use it for more simplified use cases as well. And this gives you also a new perspective on the costs associated with it. So you don't have to deal with different simplifications, makes it difficult to compare between. And so once you have invested in the large solution, then you have replaced all the simpler ones as well.
Excellent, thank you. Thank you very much. Andrea, you're next, sir. What tire characteristics do you feel are most important to include in a tire model to ensure accurate and realistic responses in a simulator environment?
Yeah, thanks for the question. I think it's very challenging to be able to provide useful information on such complex topics. I think that first of all, in the last 5-10 years, we have reached a good level of reliability in the tire models, and this, of course, means also a good level of realism, especially for DIL application. I think that we reached this level because engineers and technicians understood that the tire modeling plays a crucial role in the vehicle modeling, because I would say that a good percentage of realism passes through the point of contact between the vehicle and the road, which are the tires. So I think that the effort that has been put in the last 5 years helped us to reach a good level of correlation with reality. There are different aspects that come into my mind when we talk about realism. I think that we could focus, for example, on the point of contacts that there are between the driver and the vehicle, which, for example, is the steering wheel. So the steering response is something which is crucial to guarantee a good realism. Of course, this is strictly interconnected with the tire model and, for example, with the saturation effect, and with the capability that we have to reproduce the tire road interaction characteristics also, for example, in the peak zone and onwards, because, you know, the driver has its own reference in the reality, and we must not tempt the driver to overcome a limit of a tire model just because he is in a virtual world. Right. So I think this is very important. This makes all the difference between a video game and a well modeled tire model. Then, of course, all the multi-physical aspects that characterize tire road interaction, I think, are important to replicate what happens in the real world. So I imagine of the thermal evolution of a tire and the thermal response on forces dynamics, which is something very important, for example, especially for highly motorsport level, as well as wear, for example, both for motorsport application, but also for durability and safety investigation. But I think that the real answer to your question is either in the real contact, in the local contact between the tire, the contact patch, and the road. So I think of the capability that the road has to influence the tire and to, for example, different level of PSD, different road roughness, how they can affect and influence the tire performance. We are we're studying and we are going to publish interesting things regarding the correlation between the road properties and the tire frictional behavior, and also, which is of course strictly interconnected on the realism. And on the other side, we have the tire. So we have, for example, the local thermal degradation. We have the viscoelastic properties of the tire. We have the constitutive laws that change according to the temperature and also the frequency of solicitation. I think that all these aspects concur in guaranteeing the realism in a DIL environment. So I don't think there is just one answer to your question, but I think it is the superposition of all these aspects, and we have to guarantee all of them.
Right. Excellent.
And I think, from my experience, I can think of probably a dozen examples where we've had customers, they have a tire model, a magic formula-based tire model. They've done handling simulations in offline. Everything lines up beautifully with the proving ground test. Great correlation. Vehicle model is dialed in, tire model is dialed in, everyone's happy. You plug that into a DIM and you drive it, and the driver is like, this doesn't feel right.
Yeah, exactly.
And 9 times out of those 10 cases, it was the aligning moment model of the self-aligning moment or pneumatic trail of the tire, which was not captured properly. And that's actually a limitation in the magic formula formulation. Magic formula is not able to fully represent what happens in the aligning moment, especially in combined operations. So if you're cornering and apply a brake or apply the brakes, you get some really weird feedback based on limitations in that formulation, which more advanced physical tire models like CD tire or F tire obviously models that differently, but the steering is certainly, that to me is not the number one thing.
But I think also that if you put all the other physical phenomena on a MF-based tire model, I think things works as well. So it's a matter of how you want to see the things.
From my experience, to characterize the self-aligning torque for all the combined condition can become very extensive when coming from magic formula, because you have to cover, let's say, a lot of combined condition, during measurements that take, basically a lot of time and take a lot of effort. While with the physical tire model, you get that as, let's say, extrapolation of the physicality of the model. In principle, the pure longitudinal and pure lateral is enough to characterize the MX that is also, let's say, influenced not only from FY, as most of the magic formula model do, but also especially from FX. It means while braking or pushing on gas, the self-aligning torque is changing, and the driver is able to feel this difference. This is also my experience. But at the end, by sure, also the delays, let's say the relaxation lengths of the tire are really, really important when coming to driving simulator. Yeah.
We haven't talked about roads in that context, so all these assumptions that Pacheco or MF tires are making is that they are always thinking in steady state conditions on perfectly flat roads. So that's not the real operating condition of the tire, and also heavily influence of the road roughness or the macro texture of the surface on the tire forces. So there, for a tire, there is not de-rolling resistance or de-aligning torque. So this all largely depends on the operating condition of the tire, and part of the operating condition is the very part of the road the tire is operating on. And so all of these simplified approaches where you're reading some peak forces from some curves and take this as de-aligning torque, that's in the actual tire, that's a distributed quantity, a time-dependent quantity. It can change with operating conditions, with wear, and all of this is intrinsically covered by a physical tire model. So you don't have to put some magic in to create something that's that's actually just a formulation. So you can prove whatever you want by feeding in the right parameters. And to my understanding, this is why this type of tire models is so much beloved, because you can easily fake whatever you want to do. Yeah, and this, when you bring it then to the driving simulator, then it doesn't feel right. But it's not been the tire that's been tweaked. It's actually the problem has been with the vehicle, and it's been covered up just by messing with the tire. And a physical tire model does not allow for this, so that may look as a disadvantage, but at the same time it's an advantage because the physical tire model is a perfect component model that can be assessed on a test rig, and there is no reason that the tire should change its behavior if you bring it from a testing machine to the vehicle. And so you can use this type of tire models just like an actual tire. You get it off the shelf and use it for whatever you want.
Okay, I'm going to move on, guys, just because I want to have some time to, I know you all want questions from the audience, so thank you, guys. Last question. You know, I've been in the industry now for probably over 35 years, and most of the time I get the question, what do you see in the next 5 to 10 years? We know where we've come from. We know how the industry has changed, you know, from where we've come from. The requirements from OEMs have changed. Driving simulators came in. This is just the start, right? So Henning, I'm going to ask this question of you. Where do you see this tire modeling effort going in the next 5 to 10 years? What do you feel is going to be most important, or things we need to focus on, particularly as it relates to the simulator? And then I'd like to give you guys a little bit of time to answer that as well, keeping an eye on the clock also. Please.
Yeah, I'll go fast. 3 things I can come to think of. The first one is increased fidelity driven by the driving simulators, which, you know, what we touched on, and whether it's physical models, where it's more advanced semi-empirical models, where it's modeling of more effects that we haven't captured, thermal, wear, etc. That's one thing. Number 2 is more about the workflow. If we think about how it works today with a tire manufacturer develops a tire gets built, a tire gets tested, a model gets built, the model gets shipped over to the vehicle manufacturer who runs there on the simulator. There's a lot of steps in between there. We're talking about virtual submissions, where the tire manufacturer will submit a tire model of a tire that may or may not have been built yet. That entire workflow, I think, needs to tighten up, especially if we're going to keep, you know, faster pace in the development. So moving from the finite element models within the tire manufacturers into something that a vehicle manufacturers can plug into their driving simulators and drive, that's an area where I think we'll see a lot of development. The last one is correlation. You know, 0 prototypes, right? At some point, we're building the physical vehicle, the physical tire. How can we ensure that what we've developed virtually is actually going to work, right? Otherwise, all of this is for nothing. We had an opportunity a few years ago working with a European customer of ours who did a lot of development on a DIM. We did all the tire modeling, we did a lot of tuning, making sure that the tire models worked really well. They built the vehicle, the test driver got in the car and came out and said, I know this vehicle, right? That was like great success. Part of that is because we had a guy working that was dedicated on the tire modeling for that. That doesn't really scale. If you need to have a person dedicated to tuning the tire model to make sure that the simulation works for every vehicle program you're running, it's not going to work. So how can we take that process and make it scalable? I think those are some of the things that we'll have to tackle in the next 5 to 10 years.
Excellent. Thank you, guys. Any other comments? We've got a couple of minutes here, and then Gary, I'm sorry, we're going to go over. You kick us off whenever I know everybody's hungry.
I agree with Henning. I would add something that with which you can simulate a secondary ride and MVH in principle.
Yeah, I completely agree with Henning. And another big challenge I think that we will have to face is also to have models that are reliable but also easy to be parameterized. So a good model, it's not just a model which behaves physically, but it's also a model which is easily usable and easily parameterizable. I think this is something that we should reach. And yeah, regarding future developments, until 10 years ago, 5 years ago, we have always spoken about performance. Now we're speaking about safety, and I think that the next topic will be consumption. So also understanding how it is possible to help the prototypation phase in order to reduce the consumption of the vehicles. If I imagine of autonomous driving and something like this, we will have the mission to reduce the consumption both from fuel and also from tires. So invest also in new materials and be able to let the model be easily adaptable according, for example, to different compound and different viscoelastic properties of each tire.
Excellent. All right, so we have finished early. But obviously, we're gonna, please, go ahead. But I was gonna say, we're not done. And I know that. So please, does anybody have any questions for the panelists here today?
My question is the following. So all that we do today for tires, we, as you guys mentioned, we build a tire, we measure it, we characterize it, and then we fit a model for that. And the models are evolving. The one thing that is hard for us to understand today, which we know is real, is a kind of a variation on that tire. Because we know that real tires, they have a ton of variation in their manufacturing. That's part of life. Elastomeric elements have that. Do you guys have any thoughts about how we can make it easier to incorporate those things into the models, like short of measuring tons of tires, to try to understand how that works?
Yeah, no, I think that's a great question. I think synthesizing tires, right? Tires that don't exist yet, maybe a tire size in between what you have data for. I think it really becomes, and I think both of these guys are going to talk about that the benefits of a physical tire model is that, hey, I want to make the belt 10 millimeters wider, or I'm going to make the rim diameter 1 inch taller. Benefits of physical tire models. I think it comes down to who is going to tune the tires, right? Are you going to design a vehicle around a tire, or are you going to design a tire for a vehicle? Are the vehicle manufacturers, do you guys want knobs to turn? Or do you want to leave that to the tire supply? So I think that's really what needs to be decided first, I feel like.
So I would say that in the last years, tire makers are getting more and more specialized to provide to vehicle makers, let's say, this kind of answer. It means they are starting to use a physical tire model. And the nice thing of the tire is that we have this structure, and you cannot decouple characteristics. For example, you cannot thinking about increasing the cornering stiffness without losing something else. You cannot thinking about increasing lateral stiffness without increasing the vertical stiffness and producing a tire that is not good anymore, for example, for durability and comfort. And let's say physical tire models, I mean, I could say FEM, not to say someone of our products in principle, allow you to understand what is this surface of conflict with the surface of characteristics. And in principle, you could start virtually to exercise, let's say, how the geometry, for example, of the tire, let's say the sides, affects tire properties. And at the really beginning of the process, you would start with a very good, let's say, pre-development. And of course, you should do this together with a tire maker, because tire makers, they are the only one that they can answer the question about if a tire can be manufactured or not, because this is the key, let's say, issue there.
But I think your question was for manufacturing variability on tires and how you capture that in simulation, is that right? Yeah. So the way we've seen it being done in the past is by measuring a large number of tires and then coming up with a statistical model on some of the key metrics and then simulating those key, basically doing a small DOE, hey, this tire is heavier and stiffer, or, for these metrics. So you get almost like a confidence in interval of this is where this tire will land, not just one number that this is the, the stiffness value. So that's what I've seen being done in the past, but maybe Jerry had more ideas.
Well, I think it also depends on what you take as a reference. So when you're looking into things that cannot really reliably reproduced in the measurement, because the influence of the testing conditions are uncontrollable to some way. So what is the reference? What is your benchmark you're comparing to? And if you redo the same measurement the other day, and then you have a certain so let me put it the other way. You would have to do the measurement a couple of times and see what range of values can be measured, and then you should add the virtual tire, and then you answer the question: could the virtual result be part of that range of results that you have been testing physically? And that's very a little bit counterintuitive, because you are used to say, how accurate is it? I'm fitting to one pre-selected version of the truth, and I'm not really sure if it's helpful to design a system around such an unreliable baseline, and then wrap your head so much around how accurate can it be. So it's more like you have a range of different truths you do not know, and maybe the result that you consider not so accurate is still in a valid range. And the tire is a complex thing, and maybe the question you're raising is not really targeting an actual problem. So I hope it's not a vehicle that makes a difference if it's drivable or not, because your virtual tire model
Right,
is...
yeah, you wouldn't hope that...
I wouldn't hope.
Yeah, you would hope that the vehicle
yeah.
would pass safety standards even within that, but yeah, you want to make sure that that your vehicle performance sensitivity is low to the manufacturing variability of the tire. Yeah. And one area there, which is interesting in terms of tire performance variation, is with, I think Andrea mentioned, is tire wear. What we're seeing is you can have a 50% variation in cornering stiffness of a tire that's brand new to a tire that's worn, especially if you look at more of an all-terrain type tire. Now factor in a self-driving vehicle with autonomous driving that's using some sort of a control system, using the cornering stiffness of that. It's a big variation in performance. How robust is that self-driving system to a very big change in tire performance? So
I'm gonna have to cut it off here, guys. Okay, go ahead.
Yeah, I think that the possible answer is also is to invest in non-destructive, fast methodologies to monitor the tires, for example, both from a structural point of view, thermal point of view, and also viscoelastic point of view. So if you have instrumentation that in a fast way can detect the condition of a tire, you can update and include this information in the models in a fast way. So we have developed these kind of methodologies at our university. So, for example, we have the Veseo to detect the compound state, viscoelastic state, and how it changes towards also the temperature, and also to assess the tire. Sometimes I think it surely happened that there was a tire that was supposed to behave in a certain way, and then it went on the track and behaved in a completely different way, maybe because of the compound that was supposed to be in a way and is different. So also invest in methodology and technology that can detect this information in a fast way is a possible way to improve the models and the correlation with the real world.
So I'm going to, thank you guys very much. I'm gonna cut it off here. I would invite anyone here to please take some time to speak to these gentlemen. I want to again thank you guys very much. I know most of you, and even Henning, you've traveled a long distance to get here. I really appreciate when we get all together, because there's a lot of really neat technology going on in the area of tire modeling, and these are the folks you need to talk to about that. So thank you guys very much, and thank you very much for listening, and thank you, Gary.
No, you can take that. Thank you very much. Yep. All right, so hey, one more last round of applause for Calspan, cosin, Fraunhofer, and MegaRide. Gentlemen, thank you for the contribution to this event. And thank you, Mike Stackpole, for being able to pull that together.